All right. Okay. Thanks again for inviting me to this conference. And I also would like to emphasize, like, I would share some notes later, and I need to somehow make them. So anyways, there will be some notes to be shared in the website of IMSA. Okay, so to continue the discussion of yesterday, I like drawing pictures. So here's our story. So we had some smooth projective complex surface, S, we called it S. We had some line bundle on it, and we had some non-compact threefold given as the total space of this line bundle over S. We were interested in two moduli spaces. One was moduli space, I called it MH of nu. Nu was a choice of a Chern character. Nu was something like R gamma N, Chern character that I picked from cohomology theory of the surface. And so this was moduli space of sheaves on the surface, moduli space of sheaves on S with this Chern character nu, and which are stable with respect to the ample polarization. So this was C1 of O of S twisted by 1. Okay, and the other moduli space was the moduli space of sheaves closely related to these OS modules. So this was, I called MX of H of V. So this was moduli space of torsion sheaves on X. So moduli space of compactly supported sheaves on X. So these are supported on the zero section of this line bundle, which is the complex surface, set theoretically, not necessarily the scheme theoretically. Okay, and today I make some examples of this. Okay, and we are interested in DT invariants. So for this moduli space of sheaves on the non-compact threefold, but nevertheless supported on the complex surface, we are interested to define invariants. And so let me just mention what is the theorem. So yesterday I talked about deformation obstruction complexes and virtual fundamental classes and so on. So this is a theorem with Amin Golampur, my collaborator, and Yau. I think it goes back to 2018. So there was a complex E dot, and I showed you yesterday, it's in the notes of yesterday, how to reduce this complex. So it's coning off a certain trivial bundle that appears in the cohomology theory of this complex. And so we cone that off in derived category. And that gives us a suitable complex with a map to the cotangent complex of this moduli space. And I call that complex E dot reduced. So there is a complex, and in my notation, this was a certain truncation of the complex C dot, which I defined yesterday. Again, it is in the notes. So we proved that this thing is the virtual tangent bundle of obstruction theory over this moduli space MXH of V. So what does it mean again, virtual tangent bundle? It means that it's an object in the draft category of the whole moduli space. It has cohomologies. One by one, its zero cohomology captures tangent space to the moduli space, so deformations of sheaves that the moduli space parameterizes. And then it has a first cohomology, and that's the obstructions to those deformations, but it doesn't have other obstructions. So it doesn't have obstructions to obstructions. It's perfectly obstructed. And okay, so this is just enough to define invariance. So here's now, to continue the discussion of yesterday, I make a remark. So here's a remark. So rank of this complex, rank of E dot reduced, is the rank of original complex, which I defined yesterday, E dot. That was R hom. So this moduli space comes with the universal sheaf. So you can take homomorphisms, R hom, in the draft category, R hom, E tilde, comma E tilde, and you can push it forward onto the moduli space and shift it by 1. That is what our E dot was yesterday. So because I've taken some trivial piece out of this first cohomology theory of this complex, you can, compare rank of E dot reduced and E dot. And so it just turns out as a result of calculation that this is what the comparison is. The two have ranks which differ by arithmetic genus of the surface. So in particular, if arithmetic genus of the surface is equal to 0, then E dot and E dot reduced are the same thing. Okay, so this is the theorem yesterday that if the arithmetic genus is bigger than 0, then in the first cohomology of this complex, I see a trivial bundle of rank equal to PG of S. And so that's why. So when we take that out, the rank of the complex, in fact, goes up. Okay, so anyways, the fixed part, then fixed part of the virtual tangent bundles, are only affected by trivial bundle of rank equal to PG of S, arithmetic genus of the surface. Okay, so why is it, you might say, that E dot reduced has, by the way, why is this thing has rank bigger than E dot? Because imagine that you have a complex, it has only 0 and 1 cohomology, its rank is its degree 0 cohomology minus degree 1 cohomology, and the trivial bundle appears in the degree 1 cohomology. So if I take that out, H0 is still the same, but because the rank is dimension of H0 minus dimension of H1. So if I'm taking something from H1 cohomology, then the rank increases. That's why our rank of E dot reduced is in fact bigger. Okay, so that is that. Now here is a corollary. I said that both of these complexes are being acted on by the action of C star. So E dot fixed, the fixed part under the action of C star of E dot reduced gives a perfect obstruction theory on the fixed part of the moduli space under the action of C star. Okay, and hence a virtual fundamental class. So this is just a statement saying that you have a non-compact moduli space, and this obstruction complex on the moduli space has a fixed part and a moving part, okay? And the trivial bundle, in fact, which we keep talking about and which we need to take out in order to get the non-zero invariance, is only affecting the moving part of the obstruction theory. So the fixed part of the obstruction theory is going to be unchanged. Okay. So long story short, you will get a virtual fundamental class this way with this reduced obstruction theory. So this is virtual fundamental class of the C star fixed locus of moduli space, and it's given by this modified reduced obstruction complex. It's a homology class that sits in the Chow homology of your moduli space, the torus fixed locus of your moduli space, like this. It's a class, and then you can use this class to define the Donaldson-Thomas invariant. So this is what it is. It depends on the data of the ample polarization on the surface, because again, for us, stability of sheaves is always captured with respect to some slope after I push forward those sheaves onto the surface. It is depending on the choice of churn character, and it's depending on the choice of appropriate cohomology class. So this is given by an integral like this, and I just put this virtual fundamental cycle down there, and then I define something similar to Atiyah but localization formula. I am integrating cohomology class alpha, but I'm localizing with respect to C star. So there's always something that comes in the denominator, and that something is the Euler class of the moving part of the obstruction theory. And what is this thing? This will be some kind of a polynomial with rational coefficients, which is written as a Laurent polynomial in some equivariant parameter S. Okay, so alpha again will be an element of the C star fixed C star equivariant cohomology of our moduli space with rational coefficients. And as a ring, we need to localize this ring at an equivariant parameter. So everything that this invariant that you get will not just be a number, but it will be numbers coupled with coefficients given by combinations of S and S minus 1. So it will be a Laurent polynomial in S. Okay, so this is the definition of the Donaldson-Thomas invariant of sheaves on a non-compact threefold set theoretically supported on the surface. They could be scheme theoretically supported on surface. When we say that, it means that our sheaves are OS modules, but set theoretical support means that they could be things that can thicken outside of the surface. So for instance, you can have a curve that thickens outside of the surface. It has some deformations outside, and you look at the structure sheaf of that curve. That's an example, and many other examples like that. Okay, so now I will make connections to physics as I promised yesterday. So here is a story about Vafa-Witten invariants. Vafa-Witten invariants. I will be brief in here. So Tanaka and Thomas are the people who define these things mathematically. So Tanaka Thomas define Vafa-Witten invariants by constructing a symmetric perfect obstruction theory. So it means, perfect obstruction theory, So what is symmetric? Let's say their obstruction theory, let's say, is G dot. It's a complex. It gets mapped to some moduli space. I haven't told you what moduli space it is. I put it as, question mark in here. But being symmetric really here means that this complex satisfies the condition that if I dualize it in the derived category and I shift it by one, it gets quasi-isomorphic to itself. That's what it means, symmetry. So Tanaka Thomas defined for some moduli space in the same geometry that we are talking about, a surface sitting as a zero section of a line bundle in a non-compact threefold, some obstruction theory for some moduli space. So what is that moduli space? So over moduli space of Higgs pairs. Okay, let's call these things G and phi on the surface such that trace of phi is equal to 0. So what is phi? Phi is the Higgs map. So Higgs pairs are objects like this. So there is an endomorphism algebra of some sheaf G on the surface together with the map to twist up this thing by the canonical bundle of the surface. So this is what the Higgs pair is. And we would like the trace of this Higgs map. So this is the Higgs map. And we would like the trace of Higgs map to be equal to 0. In the language of physics, they call it, massless Higgs masses or things like that. So which kind of refers to the trace of this map to be equal to 0. So, okay. So we can call this thing M Higgs. So this is our moduli space of Higgs pairs. This is parameterizing objects like this. So I'm going to replace in here the M Higgs. So, okay, this moduli space parameterizes objects like this, and the morphism algebra of G twisted by the canonical bundle of the surface. They define some nice obstruction theory, it captures deformations of these pairs and the obstructions to those deformations. And it's constructed in a way that it satisfies this duality in derived category. So it is symmetric, perfect symmetric obstruction theory. So this for them, invariant that this thing induces, the virtual cycle and integration against the virtual cycle, that this thing induces is the definition of the Vafa-Witten invariants. And of course, the Vafa-Witten invariants originally in the physics context were defined by Vafa and Witten in the 90s. Okay, so now some facts, maybe. So fact one. In fact, Tanaka-Thomas show that moduli space of Higgs pairs is isomorphic to the moduli space that we have been talking about, mx h nu, when x is equal to the total space of the canonical bundle of the surface. So okay, this is interesting. Seems like our moduli spaces are isomorphic to each other. On one hand, we have torsion sheaves supported on a complex surface in a non-compact threefold. And on the other hand, we have some Higgs pairs on the underlying surface, and these two moduli spaces are related to each other, and in fact isomorphic. Fact two is the moduli space of Higgs pairs is equipped with a C star action. The C star action equipped with a C star action, and which is the same as C star action on the moduli space we defined. Okay, and then fact three, over the fixed locus, over the C star fixed locus of M Higgs. Okay, what we see is we can show that the trace of the Higgs map becomes equal to 0 automatically. And as a result, the C star fixed locus of M Higgs is identified with MXH nu C star. So the locus where they are interested in is not just all the Higgs pairs, which are some map from G to G tensored with canonical bundle, but it's the part where the trace of the Higgs map vanishes. And this actually becomes automatically satisfied over the C star fixed locus. Okay. Then the fact 4 about observations that came out of the paper is that the fixed part of Tanaka-Thomas obstruction theory is equivalent, that is in K theory actually, in K theory of the moduli space is equivalent to the fixed part of the obstruction theory that I was just talking about. So this reduced obstruction theory that we defined in our work with Calabi and Yau, we see that the fixed part of Tanaka-Thomas theory is equivalent to it. And this is something that we showed in our paper. And the moving parts differ, that is also in K-theory. The moving parts differ by a trivial bundle of rank equal to arithmetic genus of the surface. So in fact, in K-theory, if I look at these things, these are objects of deformation obstruction complexes are objects in derived category. You can take the K class of an object in derived. So think about the complex of sheaves, and you can look at the K-theory, K class of that complex. So in K-theory, if I give you E dot, the K class of that thing is the class of zero cohomology minus the class of the first cohomology. So if I write everything down in K-theory, you can see that. So in fact, in K-theory, I can compare the two. So H0 of the E dot reduced is the same as H0 of E dot of Tanaka-Thomas dual plus let me see. So I think something like PG of S times class of the canonical, something like that. And then H1 of E dot reduced is H1 of E dot Tanaka-Thomas. Dual. Sorry, I'm putting duals out inside, but I should put them to outside. Okay. So what is the consequence of this fact? You know, by the way, here, I'm just talking about, give me a second, my pen is not writing this. Okay, for some reason, okay, it's writing. So as a result of this, you can see that the virtual cycle of the C star fixed locus of Tanaka-Thomas is equal to the virtual cycle of the moduli space I just defined. H nu is C star fixed locus, which is obtained from reduced obstruction theory. So what is the consequence of this thing? As I mentioned to you, the Donaldson-Thomas invariance of these torsion sheaves is equal to integral against this class, this guy in here. So, and that was integrating some appropriate cohomology class alpha, and then you divided by the Euler class of the virtual normal bundle. So if I wanted, when alpha is just equal to 1, the you know, upshot of all of this discussion is that the Donaldson-Thomas invariant of this X equal to the total space of the canonical bundle of the surface, which depends on the polarization on the surface, a choice of a Chern character, and then alpha equal to 1. So this is equal to alpha. This becomes equal to the invariants that Tanaka-Thomas defined, which are equal to, by construction, to Waffle-Witten invariants. So Waffle-Witten invariants also depend on this choice of polarization. They also depend on the choice of the Chern character. But, you know, we have some differences in our construction and you know, Tanaka-Thomas construction. These differences are here in these bundles whose, you know, K-theory class is arithmetic genus of the surface times the class of the canonical bundle. So our invariants are just different from their invariants up to an equivariant parameter. So up to the S that I just defined before, to the power minus PG of S. So this is our equivariant parameter. So this is the upshot of this construction, and you can see the detailed calculation of this thing in our paper that I mentioned with Golampur and Yau in 2018. Okay, so this is what it is. So if you want to define Waffle-Witten invariance, you have two ways of doing this. You can use construction of Tanaka-Thomas, in which case you will use some obstruction theory, which is symmetric, and for the moduli space of Higgs pairs on the surface, or you can use our construction, and you can look at torsion sheaves on the noncompact threefold. And it just happens to be the case that our Donaldson-Thomas invariants kind of are compatible and equal up to a covariant parameter to Tanaka-Thomas invariants, which are the mathematical definition of Baffle-Witten. Okay, so now let me tell you a little bit about fixed loci. So all of these invariants are defined by integrating over fixed loci. So we have some Donaldson-Thomas invariants, which is roughly speaking some s to the minus pg of s times Baffle-Witten invariants, and these are equal to integrals of, let's say, 1 over the Euler class of some virtual normal bundle. So that is the moving part of some obstruction theory, and this is our moduli space, the torus fixed locus of our moduli space that defines our invariance. So let me show you a little bit of what these sheaves are, for instance. So let's do some lower dimensional analog of this space. So let's say I want to show you some of these modules, and so that I can show you what is the torus fixed loci. So here the question is, what do the torus fixed loci look like? So what are these things after all? What do they look like? Okay, so in order to show you this, I need to make an example. So let's say I have, I replace the surface with just a line, so something like this. So let's look at let x be the total space of some line bundle over the x-axis. So this is the affine line, okay? So this is our x-axis, and I have some non-compact twofold rather, okay? And this is some line bundle on there. And I would like to, I'm interested to looking at sheaves in the category of compactly supported coherent sheaves on this X. So, so let me just replace this by, this is our affine line, something like that. Or the projective line, you can call it P1 if you like. So at this point, it doesn't matter. Okay, so we have something like this. So I would like to show you some of these sheaves. So for instance, as an example, some of these sheaves are like this. So if I pick the structure sheaf of the base P1, that's a compactly supported coherent sheaf. So a structure sheaf of P1. So how is that locally as a module? The structure sheaf of this thing is written as C of X and Y. So if this is the Y-axis, okay, so this is the Y-axis, and this is the X-axis over here. So locally, this is something that I obtained by dividing by the ideal defining the base P1. So that's the ideal vanishing ideal of Y, because the Y vanishes on the base P1. So if I do that, then I can see that I will just get a CX module. So this is one of the examples of those torsion sheaves, which are scheme theoretically supported on the base. Now you can just think of this as an analog in the three-dimensional case, which when you replace P1 by some complex surface like P2 and look at the total space of canonical bundle of P2 or any line bundle of P2. But then your sheaves could also be set theoretically supported on the base, but not scheme theoretically. So there is another example. So this is example 1. I can look at the structure sheaf of twice P1. Okay, so what does that mean? It means that it's locally a module, which is given by C of xy divided by ideal sheaf of P1 squared. So that's what it is, okay? And this I can also calculate what it is. So locally, this thing will be something like C of, it could have a factor of C of x, but it could also has a factor of C of x times monomial y, because the y doesn't vanish. Y squared does vanish in this ring, but in this quotient ring, but y doesn't vanish. Okay, so this is important for us, as you can see. So I get this module. Now, as you can see in here, there is an action of a C star on these fibers. So C star is acting on these fibers. So wherever I see a Y, I can see the action of C star because C star is dilating the fibers. So I get some module on the base after localizing and look at the module theoretically. And I can see that this module is a graded module. It actually sees the action of C star. So here in the first term, C of X, I don't see any Y. But in the C of X times Y, I see a Y. And that Y carries the action of C star. So it has a different weight. So this is a module that sits in degree 0. And this is a module that sits in degree 1 because C star is acting on the Y. It's dilating Y. So you get some graded module this way. Okay. So you can also get more. So you have C of X times plus C of X times Y. And in fact, you can get a coaction by the vertical fibers, something that gives you a Higgs map. And this is the relation between the work of Donaldson-Thomas and what we did, torsion sheaves on the threefold. So you can get a coaction, which is induced by multiplication by Y, which just, if you multiply the first term, you will get the second term like that. And then you can multiply the second term and you will get Y squared. But in fact, this thing is equal to 0. Why? Because this whole thing is this quotient ring divided by ideal of Y squared. But nevertheless, you can see that you get something which is very similar to a Higgs bundle. So if I call this thing a G, this thing is G twisted by the line bundle, O of 1. That's our line bundle N. So in fact, it is true that we are getting something like a Higgs map down there. So as I start from some torsion sheaf on the total space of this line bundle over the P1, this torsion sheaf is supported on the base. When I localize and I push forward onto the base, I will get some Higgs map down there. Okay, so there is more to it. So actually we can also calculate what the Higgs map is. So this is a 2 by 2 matrix. The first term goes to the second term, so 0 and 1. And then basically this would be the Higgs map. So maybe something like that. This is your Higgs map phi. Okay. So this is basically the analysis that goes into identifying the torus fixed loci of your moduli space. You have a sheaf on X equal to the total space of line bundle on the surface. And this projection map is Q. If you push forward your sheaf onto the base, it decomposes as, in terms of, it decomposes into some terms, EIs. And these EIs each carry some torus weight. So I can tensor them with the trivial bundle yesterday I was talking about. There is a trivial bundle, which is equivariantly non-trivial, and it keeps track of the degree or grade of these modules, which weight space they sit in. And then I can add over I, and the whole decomposition is going to be in a way that some of the rank of these sheaves that I get down there should add up to the original rank of original sheaf. This is exactly what we got. So I started from some sheaf in here, and this is, let's say in this analysis, I got a sheaf E1 and I got a sheaf E2. E1 sits in degree 0 because it doesn't have a Y attached to it. E2 sits in degree 1, there is a Y attached to it. And so that's exactly what we are talking about here. Okay. And so therefore, if you would say, how many ways can I get these EIs? Well, the only condition that you need to satisfy is the sum of the ranks should be actually sum up to the rank of the original sheaf F. So you partition the rank of F. That's basically the idea. Okay, so this is only saying that if I look at the moduli space of these torsion sheaves on the original variety, and if I look at the torus fixed locus of this will be some union of all partitions. So if rank of F, okay, so let's write it like this. So if I look at some F inside this moduli space, okay, so actually maybe write it like this. So if nu is given by R, gamma, and N in the cohomology theory of the surface, H2I I from 0 to 2 of S with rational coefficients. This is our rank. Then torus fixed locus of the moduli space will be given as a disjoint union over all possible partitions of the rank of the moduli space of sheaves with churn character V and partitioning them in terms of the ranks. So this is what it is. Okay. So by the way, if there is any question, you can let me know now. Okay. So this objects that sits in here are exactly analog of basically this. This is this argument that I've put in here. Okay. Okay. So what does this say is that the virtual class of the moduli space also decomposes according to the partitioning of the rank of the sheaf over its support. So if you look at virtual cycle, then it just becomes union or the sum of the ranks. So it will be a sum over all partitions of the ranks of the virtual cycle, reduced virtual cycle. I can put a reduced in here and I can put a partition over there. All the different ways that you can have a sheaf F, you push it forward, and you can write it as a sum of the sheaves EI such that the rank adds up to the rank of the sheaf F. Okay, so let's do one example. Let us assume that R is equal to 2. So you have torsion sheaves whose rank over their support is equal to 2. In that case, the virtual cycle, so in that case, lambda could be 2, 0. This is a partition of the rank 2, or lambda could be 1 and 1. There is not any other way of partitioning the number 2, right? So if you do that, if you have this partition, it means that if I have a sheaf supported on the surface, so this sheaf is compactly supported coherent sheaf. If I push forward this sheaf, so here is our non-compact threefold with a map to underlying variety S, then I can push forward my sheaf like this, and it becomes the sum of two sheaves, EI, E1 plus E2. It could be that E1 has rank 2 and E2 has rank 0 as an OS module. That means it's a torsion sheaf on the surface. Or it could be, this is case 1, or it could be that push forward becomes sum of two sheaves as graded modules, each one of which have rank 1. So this belongs to this partitioning, and this belongs to this partitioning, and there's no other way of partitioning 2. Okay. Now, if F is stable, H is stable, in the sense of the definition of the stability that we just used, H stable sheaf in our moduli space, okay, then we can see that for case 1, E2 should be isomorphic to 0. Otherwise, Q lower star of F will be unstable. So this is a fact. Okay, so basically this is saying that if you have a stable sheaf, H is stable sheaf over this moduli space, then you push it forward. There is a locus, which is given by partitions 2, 0, but in fact the E2 part is just equal to 0. So this is saying that if you push forward your sheaf down onto the surface, you get some torsion-free sheaf of rank 2. So in this case, E1 is a torsion-free sheaf of rank 2 on S. Okay, so that's that. And then there is another locus where you get sum of E1 plus E2s, each one of which have rank 1. And that's allowed, basically. So only this rank 2 case is itself very, very interesting. So in this case, so just to summarize, summarize. If I look at the virtual fundamental cycle of my moduli space, the torus fixed locus of my moduli space, which is induced by the reduced obstruction theory, I can see that it becomes the sum of two virtual cycles. The virtual cycle of the H stable sheaves with that Chern character of whose push forward onto the surface becomes a sheaf of rank 2. So moduli space where Q lower star of F is torsion free and rank 2 on S, plus the component of the moduli space, which is partitioned by 1, 1 virtual reduced. This is the part where Q lower star of F becomes E1 plus E2, each one of which have rank 1. So somehow, I don't know why, in the literature, this component is called instanton branch. This part I actually know why. I mean, this goes back to the instanton theory on 4 manifolds. But somehow the part that I don't know why is this component. This is called monopole branch, and I think it is the wrong terminology, according to what I heard from Kamran Wafa, who was in one of these talks at some point, and I think I gave the talk, and then he said, "You're mistaken, you shouldn't call this thing monopole branch." But anyway, there's literature that calls this component, the 1-1 component, the monopole branch of the moduli space. Okay, nevertheless, you might see this in the literature. Okay, so in full generality, if rank of the sheaf is bigger than 1, then you can write MXH nu C star virtual reduced as a sum of virtual cycles over the R partition. That means those sheaves which are compactly supported, whose push forward is just a torsion-free sheaf of rank R on the surface. Yes, plus all the way, you have all partitions, and at the end, the last virtual cycle is MXH nu with the partition 1, 1, 1, 1, R many times. Okay, so this is basically telling you, if you want to integrate against the virtual cycle on the left side of this equality, what are the contributions? The contributions are from these sheaves, depending on how their push forward will become partitioned into sum of modules down there. Okay, now here's actually a theorem. Here's a theorem. Okay, by Ghulampour, myself, and Yau. I think this also goes back to 2018, that the restriction of MX H nu C star to the 1, 1, 1, so to this component, to the monopole branch, so 1, 1, 1 component of the moduli space. Moduli space is the nested Hilbert scheme. Nested Hilbert scheme denoted by nested Hilbert scheme of configurations of curves and points on S. This nested Hilbert scheme we called something like N1 and R, beta 1, beta r minus 1. Okay, so let me tell you what this means. Okay, we are looking at a moduli space for these torsion sheaves on the threefold. We are looking at the C star locus. We know that in the level of the moduli space, this thing becomes disjoint union of C star equivariant sheaves, which after being pushed forward to the surface, they just become torsion-free sheaves of rank R, union many other components, and the last piece is the monopole branch, so which are sheaves which partition as 1, 1, 1, 1. So sum of EIs, each one of which have rank 1. So let us look at some sheaf in here so that we can see what's the relation between this and the nested Hilbert scheme. So if I push forward this kind of sheaf onto the surface, then it becomes sum of E1 all the way to some ER. Each one of these things have rank 1. Rank is equal to 1. And remember that these become graded modules. I made an example of this thing with the structure sheaf of the fattening of the P1 inside the local surface given by some line bundle on P1. So the idea is as follows. As a graded module, you can see that you get something like this. And let's say this thing sits in degree 0. Next term sits in degree 1. And as graded modules, let's say this thing sits in degree R. Example of this thing you saw before when I had the sheaf was C of xy, quotient by y squared, and it became C of x plus C of x times y. This was an example. So this thing sat in degree 0. Next one had a y coupled to it, so it was sitting in degree 1 as a graded module. If I had y to the cube, for instance, I would have a term C of x times y, plus C of x times y squared. So you can see that you can have a term sitting in degree 0, then degree 1, then degree 2. This is basically as simple as it is. So these EIs are sitting in degrees, different weighted spaces as graded modules over the action of the C star. And also, we saw that there is this coaction which induces the Higgs map, right? So if you have some sum of EIs, E1 to ER, sitting in different degrees, then there is this twisting by the line bundle that gives you the Higgs map. E1 tensored with L, it keeps going, ER tensored with L. Now you can ask yourself, what are the torus fixed? So there is a locus like this. As soon as you push forward the sheaf, you get some locus of Higgs pairs like this downstairs. And now you can ask yourself, what are the torus fixed sheaves? So I would like to know, as a set, what the torus fixed objects look like in here. Okay, so if I have, so as an example, if I have E1 sitting in degree 0, E2 sitting in degree 1, I will get E1 times L plus E2 times L by multiplying by the functions along the fibers. And the point actually is that L itself carries a torus weight, non-trivial torus weight. C star is acting on the fiber. So if I tensor E1 with L as a graded module, it sits in degree 1 because it moves. This is, in our example with the P1, it is like multiplying by a factor of y. And the next one sits in degree 2, for instance. Now you can ask yourself, what are the C star fixed pairs or Higgs pairs that I can see in here? If you have a morphism between graded modules, the C star fixed morphisms are the ones that take some weighted modules to the weighted modules which sit in the same weighted space. The only possibility for this in here is you get non-trivial maps from E2 to E1 times L. Why? Because E0 is sitting in degree 0, nothing on the right-hand side sits in degree 0, and E2 times L is sitting in degree 2, nothing on the left-hand side sits in degree 2. So in fact, the torus fixed pair that we get in here is the E2 going to E1 times L. Why? Because E2 is sitting in degree 1, and now E1 is also sitting in degree 1. But then remember that E2 is rank 1, and E1 is also rank 1. If S, the phase surface, is complex, smooth, projective surface, then there is a fact, very simple fact, that such such EIs will be ideal sheaf of bunch of points, ideal sheaf of points, maybe up to a twist by some line bundle. Let's call that line bundle M. Some line bundle. So these will be torsion-free sheaves of rank 1 on a smooth complex surface, or twisted ideal sheaves, actually. Okay, so this is interesting. It seems like over the monopole branch, push forward of our sheaf becomes somewhat Higgs pairs, whose torus fixed loci are given by pairs of basically the morphisms between twisted ideal sheaves. So if I rewrite everything in here, so let's say this becomes something like ideal sheaf, some N2, many points, twisted by line bundle M2. And this becomes, E1 becomes ideal sheaf of N1, many points by some line bundle M1. Now, of course, there is this L in here. Okay, I can actually, because these are line bundles, N2 is invertible, so I can actually move it to the other side. So I have a map from ideal sheaf of some N2 many points to ideal sheaf of N1 many points, together with a divisor, right? So it's something like a M1 tensor with M2 inverse tensor with L. Some twist of an ideal sheaf of N1 many points on the other side. So in fact, considering a stability condition and so on, because this object is a consequence of pushing forward the stable sheaf on the torus fixed locus of the moduli space of torsion sheaves, you can actually see that the stability forces this morphism to be injection, this morphism to be injective. So this becomes a nesting of ideal sheaves of points together with, I mean, this itself could be some divisorial ideal sheaf, because these are divisors. You can call this thing I of some minus D for some divisor D, or O of minus D, OS of minus D by some divisor C. So you can actually see that when you look at the torus fixed locus of the moduli space, you have some nesting of ideal sheaves of configurations of points and curves inside this complex surface S. And this is exactly the nesting of subschemes. And that's why we call it nested Hilbert scheme. Okay, so this is the relation to the Hilbertism. So you somehow, if this is your surface, you have some divisor D, so maybe a bunch of points on the divisor, on the Cartier divisor, together with some bunch of points outside. And so you're basically looking at pictures like this. So this is our ideal sheaf of N2 many points twisted by some divisor, and it injects inside ideal sheaf of N1 many points twisted by some other divisor, D1, D2, maybe something like that. Arrow gets inversed because I'm looking at functions vanishing on those things. So this is exactly the nested Hilbert scheme. This is the relation to the nested Hilbert scheme. Okay, so in the last 5 minutes, I just mention for you what are in the level of invariants. So the upshot of the story is that you look at torus fixed locus of the moduli space of torsion sheaves on a non-compact threefold. This torus fixed locus becomes a disjoint union of many components based on the partitioning of the rank of the sheaves over their support. There are two components which are interesting: instanton branch, which is the branch where push forward of the sheaf just become an honest rank R sheaf on the base. And there is many components in between. And then there is a last component, which is monopole branch, where the rank of the sheaf has a partitioning of 1, 1, 1, 1 R many times. And that's a nested Hilbert scheme. Okay, so contribution of invariance is from all of these things. But in particular, when rank is 2, so here is a theorem. So this is, again, Gholampour, myself, and Yau. I think this was 2017, I believe, when the Chern character of the sheaf is given by 2 gamma n, meaning the torsion sheaves have rank 2 over their support, then there is only instanton branch and the monopole branch. And so you can actually see that the Donaldson-Thomas invariant of, with this choice of Chern character, becomes Donaldson-Thomas invariant of the instanton branch plus contribution of the nested Hilbert schemes. So basically this becomes sum over N1, N2, and the class of the difference of the classes of divisors D1, D2 in this picture. Maybe we call this thing in our paper beta. It looks like the difference of class of D1 and D2 of some integrals. So let me put the integral in here. Some integral of class alpha over the nested Hilbert scheme of N1 and N2 points together with D1 and D2, whose difference is beta, which is the nested Hilbert scheme. So these are invariants of nested Hilbert schemes. Invariants of nested Hilbert scheme. Okay, so in the last 2 minutes, maybe I actually mentioned some things from you. So left-hand side of this equality is Vafa-Witten invariance, as I mentioned, up to some equivariant parameter. Right-hand side has contributions from instanton branch and the monopole branch. And in fact, there is more to it, some interesting results. So it turns out that these Donaldson-Thomas invariants of rank 2 sheaves on the surface, these become sum of Seiberg-Witten invariants Seiberg-Witten invariance of the surface coupled with some combinatorial coefficient. So A is a combinatorial coefficient, which has a long definition. I'm not going to put it in here. Okay, and the correction term in here is this invariance of nested Hilbert scheme. Okay, the point of this analysis and importance of this analysis is that in the original paper of Vafa-Witten, it was conjectured that the Vafa-Witten invariants have a partition function which is modular form, has modularity property. So there is modularity that you can see on the left-hand side of this equality. But there is no statement about modularity property of Seiberg-Witten invariance, for instance. But doing this analysis, you can actually see that there are some cases where the monopole branch, these integrals that I've just defined in here, just contribute 0. So they vanish. And so even though Seiberg-Witten invariants have no modular partition functions, it seems like a modification of those things, which is some coupling with some combinatorial coefficients, do have modularity property. Because the left-hand side is modular, so the right-hand side should be modular. That's one interesting fact about this equality, about this proof. The other fact which is interesting is also that this maybe reminds us of some effort which was done for many years, and I think it's still, people are working on it, which is about invariance of 4 manifolds. So I know that Cliff Tops, for instance, has been working and has many results on proving that the Donaldson invariants of 4 manifolds are related to Seiberg-Witten invariance. So this is not as complicated as that. This is a holomorphic version of that. So what we are saying is, well, it's not true that necessarily Donaldson-Thomas invariants are Seiberg-Witten invariants, but it seems like they are related to Seiberg-Witten invariants together with correction terms. And the correction terms are invariants of nested Hilbert schemes. Finally, the last fact is that sometimes invariants of nested Hilbert schemes themselves have partition functions which are modular. And all of this we have discussed in our paper. So in that case, Seiberg-Witten invariants are given by the difference of something which is modular on the left minus contributions of modular invariants of nested Hilbert schemes. Again, it's some other modularity property which is also being investigated by many people, I assume, including ourselves. Okay, so that's it. And I think I did relate invariance of torsion sheaves to flags. What I meant by flags are the flags of these kind of flags. This very much looks like a flag. And finally, I would like to add a comment that just the analysis I put in here is just for the case where the rank R is equal to 2. So the flag you get over the monopole branch is the flag of ideal sheaves. Obviously, if R is bigger than 2, you can do the same analysis looking at the torus fixed loci of the moduli space. You get flags of sheaves, EI sitting inside EI plus 1 tensor with a line bundle, that's sitting inside EI plus 2 tensor with a line bundle, and so on and so forth. But you might not necessarily have the fact that the rank is equal to 1. Those are the other components. Nevertheless, they are flags. And there was a paper that I wrote with Yau and myself last year in 2019, which had high rank flags and Waffle-Witten invariants, which actually studies the contribution of those other components. It's actually difficult to construct well-defined deformation obstruction complexes over those components and then defining invariants. Anyway, so there is this paper. Thank you again for inviting me to this conference, and I hope that you can get some interested in this topic, and maybe especially younger people can continue it. I will provide the notes to the organizers so that you can have access to them. Probably those are prettier to look at. Anyways, I stop here. Thank you.
Thank you very much.